Today we're going to take a look at lesson 4.2, which comes from Math in Focus, the 6th grade textbook, and we're talking about equivalent ratios. And I had a lot of students request videos on this, so it leads me to believe that they have some concerns. So I'm just going to run through a few examples to try to get them started, or try to get you started. If you're taking a look at this video, hopefully it kind of gives you some clues about what we're looking for. So for this first section, it says we want to express the ratio in simplest form. Well, I hope you remember from our lesson today, when I'm simplifying, I'm really looking at dividing. And ideally, I want to divide by the greatest common factor. So if you can't find the greatest common factor, don't be afraid to take a couple steps along the way, but that would kind of be your ultimate goal, so that maybe you can avoid extra steps if you know, possible. Numbers 1 and 2, I'm not too scared about. I hope that you notice that we've got a couple even numbers happening here. You probably could start up by dividing by 2, unless perhaps you notice that there's a greater common factor that could work first. I'm going to fast forward to number 3. If you take a look, I have 45 to 90. That's how we would read this ratio. And a ratio is really a comparison. So it might mean I actually have 45 flowers and 90 cacti or something that I'm collecting. But I can also simplify a ratio so that I can just show you what the comparison looks like in its smallest terms or lowest terms. So I want to divide. I want to come up with the greatest common factor that goes into 45 and 90. You really could use a multiplication chart at this point, but I notice one number ends in 5 and one number ends in 0. That's a hint to me. I know I can divide by 5. Let's see where that gets us. Well, 5 goes into 45 9 times. 5, 10, 15, 20, 25, 30, 35, 40, 45. Yep, 9 times. And 5 goes into 90, but I'm not sure how many times. You could try a couple things to get there. I could take that 90 and divide by 5, and using long division, I could find a solution, or the second term of my ratio. Another way to think of this is to do number bonds. I could take 90 and split it into some friendly numbers. Maybe I could split it into 50 plus 40. The reason why these are friendly numbers, I can really divide 50 by 5 and 40 by 5 pretty quickly, right? So doing this, I know 5 goes into 50 10 times. I know 5 goes into 40 8 times. And if I were to combine those, well, 10 plus 8 is actually 18. It looks like I'm going to get an answer of 18 for that second term. Well, you want to ask yourself, did I really find the greatest common factor, or can I divide again? And in this case, you might notice, oh, even though one number is odd and one number is even, 9 and 18 appear in the same row of your multiplication chart. Oh, I see that they're in the 3 row. I could divide them both by 3. Oh, but they're also in the 9 row. I could also divide by 9. Let's grab that larger factor and try dividing again. So what times 9 gets me 9? The answer would be 1. And you'd say, what times 9 gets you 18? The answer would be 2. If you notice, I have a ratio, and it has a 1 in it, so it's as low as you can go. Sometimes we would call that the simplest form of a ratio. Okay, we reduce the ratio to its lowest terms. This is a final answer. You might go back and say, well, how come that took me 2 steps to get from here to here? How come I couldn't just go straight from 45 to 1 and 90 to 2? Well, you might notice that when I divide by 5 and then divide by 9, that's really the same as dividing by 45. There is one group of 45 in 45. But there are 2 groups of 45. 45 times 2 is actually 90. So I would say 90 divided by 45 gets me this 2. We actually found the greatest common factor in looking back. Okay? And if you don't see that the first time through, that's okay. Take multiple steps until you get there. I'm going to fast forward to number 5 and 6. I know that we're having some trouble with these conversions. I know my students are kind of fighting with this idea. So the good news is weeks and days, we're pretty familiar with that. Weeks are longer than days. So I'm going to grab the longer unit or the larger unit, and I'm going to write down 1 week, and I'm going to write down its conversion is the same as how many days? Well, if you have to count them up, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, you would find that there are 7 days in a week. What that means is in the first week, I'd find 7 days. And the next week, I'd find 7 more days. And the following week, I'd find 7 more days. It sounds like I'm getting more and more, or I'm multiplying. I want you to take your 20 weeks times 7 days, and we're going to turn this into strictly days. What would I get? Well, hopefully you see 2 times 7 is actually 14. But there's a 0 back here, so that's going to get me 140 days. And this 14 days, well, it gets to stay the same. I now have days compared to days. I really have like units. So I'm ready to simplify. I want to write this ratio in simplest form according to the directions. So I notice that there's a 14 in both of these. Oh, I think I could divide them both by 14. I'm going to show an equivalent ratio kind of next to this because I'm running out of space here. Don't want to run into my words if I can avoid it. Well, I know 14 times something would get me 140. I see this 0 at the back. Oh, it's like saying 14 times 10. And then if I look, I would say, how many 14s in 14? And the answer would be 1. I can make one group. This looks like it's in its lowest form or lowest terms. I have simplified my ratio. And I know that because 1 is as low as we can go in ratio form. It's kind of like the limbo, as low as you can go. The next thing I want to take a look at is number 6. So we have a different type of conversion here where we're talking about ounces and pints. You would find this on page R8 of your planner. So page R8, 6th graders, take a look. It's in the reference pages of your planner. I also gave a handout to a couple of my classes, so you would be able to find ounces and pints there. Well, you're going to find these underneath probably capacity. I'm thinking that's what they're calling this section. And you might also think back to the gallon man that I drew with you. The gallon comparison. It's kind of a visual device to help us remember. Inside the pints that we drew the other day on your notes packet, we would find 2 cups. And inside each of those cups, we would find 8 little ounces. So if you wanted to tell me how many ounces are hidden inside my pint, I see 8 and 8 more. That actually makes 16. So one way of going to a conversion in this case is to find the larger unit. The larger units are pints. They're bigger than ounces. And inside each pint, I'd find 16 little ounces in the first one, 16 little ounces in the next one. I would find 16 ounces 8 times. I'm going to go ahead and use this multiplication to get there a little bit quicker. So notice I already have ounces on the first term, so I'm going to keep that 32 the way it is. But this 8, it's going to change from pints to ounces. I'm going to multiply. And I know 8 times 10 is 80. 8 times 6 is 48. 80 and 48. Trying some quick number bonds here. Looks like I'm going to get 128. Now this won't be a final answer, but at least I have the same size units. Now they're all in ounces, those tiny little unit of capacity. So next I need to think about simplifying. What's the biggest number that divides into these 2 numbers or into my ratio? Well, I see I need to kind of erase my drawing and my work here, or else I might need some line paper, which I cannot easily get because I'm working on the Promethean. And I'm fighting with my toolbar, so let's see if we can get that back. Here we go. Let's try a little bit of an erase here. Schumann size erasers. There we go. And I'm trying to find maybe 32 and 128 in the same row of my multiplication chart. I'm not sure if that's going to be possible or if it's going to go off the charts. I think it might go off the charts. So I noticed something. Both these numbers are even. I know I could start by dividing by 2. I'm guessing that's not the greatest common factor or the biggest factor, but it probably will get me started. So how many 2's in 32? Well, you could do that with long division, so we talked about that before. I could take 32 and divide by 2 and see what you get. Or another way to do this might be number bonds. So 32 is really the same as 20 plus 12. And I really can divide these nice numbers by 2, so that's why I chose to split it into 20 and 12 more. Well, what happens here? What's half of 20? 10. What's half of 12? 6. And 10 plus 6 actually gets me 16. So half of 32 must be 16. There we go. I'll record it. 16 compared to something else. Well, 2 goes into 12 twice, and 2 goes into 8 4 times. So it looks like I'm going to get a 24 sitting here. Check. Is this in simplest form? You'd hopefully say not yet. I still have 2 even numbers, so I could definitely divide by 2. But does something larger go into both? Ooh, I think 4 goes into 16 and into 24. That's not bad, but is there anything bigger? Oh, how about 8? 8 goes into 16 and 24. I'm going to try dividing by 8 and see where we get. Well, 8 goes into 16 twice, and 8 goes into 24 3 times. Can we simplify this ratio anymore? No. Here we go. Simplest form of my ratio. Now, we took a couple steps to get there. What would be a quicker way? what is the greatest common factor that would actually have worked instead of dividing by 2 and then dividing by 8? Oh, I could have divided by 16. There are 2 groups of 16 in 32. And if I divided this 128 by 16, there are 3 groups of 16 inside. So if you're thinking of the greatest common factor, you would need to use 16 for this problem. All right, I'm going to fast forward to the next section here. So next they're asking me to consider whether or not I can write these as a ratio. So for number 7 and 8, actually they're asking if these are equivalent ratios. Helps if you read it out loud correctly. So for number 7, I want you to notice that these ratios, well, they look like they might have some friendly numbers happening. One thing I could consider is if there's a rule to go from 13 to 30 and the same rule to go from 15 to 26. And because I don't see anything like that offhand, here's another hint. Let's try simplifying. And after we're done simplifying, let's compare. Let's put these 2 ratios in simplest form. Well, can I simplify 13 to 15? Not really. 13 to 15 is in simplest form. Let's take a look at 30 to 26. Does something divide nicely into both of those numbers? Well, I think they both divide by 2. Half of 30, half of 26. Well, half of 30 is 15, and half of 26 is actually 13. Now the question is, are these equivalent? Oh, look, they have the same numbers. You might think they are equivalent ratios. But do you notice how the 13 here is the first term, and the 13 here is the second term? They have to do with something different. They don't really match. And you notice how this 15 here goes with the second term, and this 15 here goes with the first term? Do you see how they don't really line up? This would be like saying I have 13 guinea pigs and 15 birds. But over here I have 15 guinea pigs and 13 birds. That means something different. These are not equivalent. So we might just write the words not equivalent. I want you to try the same strategy for number 8. So again, we're trying to figure out if these might be equivalent ratios. So one way to do that is to see if there's a way to go from 54 to 18 and using the same rule to go from 18 to 6. I think that might be a good strategy for this one. Or we can do exactly what we tried a minute ago. Let's simplify and then compare. So let's simplify 54 to 18. What could I turn this ratio into in simplest form? Well, if you notice, they both divide by 9. Oops, helps if I write divide by 9 here. There are 6 9s in 54, and there are 2 9s in 18. Oh darn, I didn't get the greatest common factor again, did I? But that's all right, we can divide again. How many 2's go into 6? Hopefully 3. And how many 2's go into 2? Hopefully 1. Right? Definitely 1 times 2 is 2. All right, we have this first ratio in simplest form, 3 to 1. We need to do the same idea with this next ratio. What is the biggest number that divides into both 18 and 6? Oh, I could divide both terms by 6 and see what I get. How many 6's go into 18? Well, you would say 3. And how many 6's go into 6? You would say 1. I want you to compare for a quick minute. When I simplified both of these ratios, do you notice anything? Ah, I get the same great answer. These actually are equivalent ratios. So we could say maybe yes, equivalent. I'm going to take a look at a couple problems in this next section where we're missing a term. So we're trying to find a missing piece. It's kind of like, you know, if you're trying to solve a puzzle, you're missing a small part, you try to find all the pieces to make it go together and make a beautiful picture. So we're going to try the same idea here. I'm going to take a look at number 10 and 12 just because I think that those are a good variety of things to try. And I want to take a look at number 10 first, where it says this 6 is my first term, just like 42 is my first term. This 11 is my second term, and oh, there's a second term over here I don't know. So notice I'm using some coding. I'm not saying you have to use this strategy, but I kind of like it. It reminds me that the 6 and the 42 are friends. They go together somehow. That means that there's some rule to go from 6 to 42. Also notice this. That means that 11 and the mystery number must be friends somehow. They go together with the same rule. So how would you go from 6 to 42? Well, the number is growing, so instantly you should think about multiplication. Well, what do I multiply 6 by to get to 42? I hope you're thinking 6 times 7 is 42. Well, if I just discovered the rule is times 7, I need to use the same rule here. What is 11 times 7? 77. I found the missing piece. This is all we're looking for. We just have to be very careful about which terms belong together. Let's take a look at this next one, number 12, because this could be kind of challenging, I think. So I noticed that the first term is a 3, and the first term in the next ratio is missing. That's not a very helpful piece, is it? So take a look at the next term. The second term here is an 8, and the second term in the second ratio is 72. Oh, I can find a rule from this. If you notice, the missing piece isn't helpful until the very end. So I'm going to connect the second term to its second term friend and figure out, how did they get there? Well, this number seems to be growing. They went from 8 to 72. So I know they're multiplying by 9. If you do that to the second term, you must do that to the first term. After all, we want them to be equivalent. So what is 9 times 3? Hopefully you'd say 27. That is the missing piece. There is a way to check these and see if you agree with your final answer. You really could take the answers you get and simplify them. See if when you divide them, you can get back to the original start. Well, 7 goes into 42 6 times, and 7 goes into 77 11 times. Yep, this first one checks out. And I could do the same thing with number 12. I just noticed some numbers getting rather large, so for that reason, I guess we'll take a look at number 16 before I call this section good. So here we are, number 16. Oh, these numbers are rather big. Well, let's do that coding strategy. Notice 65 is the first term. It came first in front of the colon. Next, this unknown piece is actually the first term because it happened before the colon. So those two pieces go together somehow. I don't think I can find a rule for them yet. But take a look at this. 90 is the second term, just like 18 is the second term. These are those buddies. They go together. Somehow there's a rule happening here that I need to uncover. So what I really want to say is, how many 18s are in 90? Or I notice the number's getting smaller, so I know I need to divide by something. You could try some long division maybe, or you could maybe use your multiplication chart. Let's see what we could do with some long division here for a quick minute. Oh, I don't really know my facts of 18. Well, I know it doesn't go into 9. That's good. And I'm trying to think of what times this might work. So off to the side, maybe you're saying 18 times 3. Let's try it. Well, 8 times 3 is 24. Keep the 4, regroup the 2. 3 times 1 is 3, plus 2 more makes 5, 54. Oh, not close enough. I better try again. All right, let's rethink that. What about 18 times 4? Well, 4 times 8 is 32. I'll keep the 2 and regroup the 3. And 4 times 1 is 4, plus 3 more makes 7. 72. Oh, I'm pretty close. Do you think I can get closer? I'm going to try using 5 and see what happens. What's 5 times 10? Hopefully you'd say 50. And what's 5 times 8? I think you'd say 40 more. 50 plus 40. Oh, 90. We're using some number bonds to get there. Oh, actually, they must have divided by 5. The rule to go from 90 to a smaller number like 18 is divide by 5. If you do that to the second term, you must do that to the first term. The rules have to look the same to stay equivalent. And I know I want these to be equivalent because there's this equal sign sitting here. That's a big clue also. So I want to say how many 5s are in 65. Or I could try some long division. 65 divided by 5. Or I could try some number bonds. 65 is really the same as 50 plus 15. And I know 5 goes into 50 10 times. And 5 goes into 15, oops, I wrote that wrong, 3 times. So 10 plus 3 is actually 13. The missing piece here is 13. And I first found it by using the two numbers that were both in the same position or in the second term. They gave me the rule, and then I used that same rule and apply it to the first term to find the missing piece. We're going to fast forward to this bottom section. So number 17 and 18 is where we got to stop tonight. Let's take a look at those next. All right, so number 17, I need to find the equivalent ratios. All right, I know equivalent means I want them to have the same value, so I can use an equal sign if I choose to. Number 17 says, let's use division. Oh, key word. I'm going to underline it or highlight it and show you what it means. I want to find all, that's an important word, all the whole number ratios equivalent to 56 to 24. That really means that I want to divide this 56 by 24 as many times as I can. I want to use as many tiny little factors as I can until I can find all of the possibilities. So to do that, I really would suggest that we go back to, well, it was actually Unit 1 long ago, and build a couple T-charts. I want to divide these numbers by as many factors as they have in common. So 56 is the same as 1 times 56, and 2 times, let's see here, half of 50 is 25, and half of 6 is 3 more. So 2 times 28 should work. Does 3 go into 56? No, it's not on my chart, and 5 plus 6 is 11. That doesn't divide by 3. What about 4? Oh, I think 4 goes into 56. In fact, 4 goes into, let's break this up, to 40 and 16. 4 goes into 40 10 times, and 4 goes into 16 4 times. Oh, 10 plus 4, 14 times. All right, what about 5? No, they don't end in 5 or 0. What about 6? No, 6 times nothing is 56. How about 7? Oh, there's a fact I hope you know. 7 times 8 is 56. And I know I have them all because there's no number between 7 and 8. And I didn't miss any. I didn't skip around. I went right in order as I did my T-chart here. Let's take a look at 24. Let's break it into pieces or factors. 1 times 24 would be a great start. And I also notice it's even. So what's half of 24? Half of 20 is 10. Half of 4 is 2. That would make 12. 2 times 12 is 24. Does 3 work? Well, I think you can find it on your chart, or maybe you know a fact, or you might notice 2 plus 4 is actually 6, and that divides by 3. So yep, 3 is a factor. 3 times 6 is 18. 3 times 7 is 21. 3 times 8. 3 times 8 is 24. All right, what about 4? Yep, 4 will work. 4 times 6 is 24. How about 5? No, doesn't end in 5 or 0. That's no good. And in fact, that's the only factor I'm missing between 4 and 6. I've got them all. So your next step is really to decide, ooh, what do they have in common? Well, they both share a 1. Although, keep in mind, if I divide these factors, if I divide this ratio by the factor of 1, it won't change the numbers much at all. So we're going to kind of skip that 1 for today. But I notice they both share a 2. So I can divide both these numbers by 2 and see what we get. Well, what's awesome is you can look right across, and half of 56 is 28. Half of 24 is 12. Looks like I could write a brand new ratio, an equivalent ratio of 28 to 12. This is one good answer. But it says to find all of them, so let's keep on going. So we took care of the 2. Next, I should probably look for another common factor. Well, they don't both have 3s, but they do both have 4s. We can divide both of these numbers instead by 4. Oh, what's awesome is I might not know how many 4s go into 56, but if I go back to my T-chart, it's right there, 14. And if I go back to my T-chart for 24, 4 times 6 will work. So let's write that, 14 to 6. That's another good answer. Also, if you take a look, it's kind of like we took this ratio that we had a moment ago, and we split those numbers in half, didn't we? All right, are there any other common factors that we should consider? Do they both have 7s? No. Oh, they do both have 8s, so 8 on this T-chart. Oops, and I'm done with the 4. I can cross that off. Let's divide both of these ratio terms by 8. Oops. How many 8s in 56? Oh, look across from the 8. I notice there's a 7. And if I look across from the 8 on the 24 T-chart, there's a 3. This is kind of a funny spot to put that answer, so I'm going to write it over here instead. I believe I have all of them, and I say that because when I look back at my T-chart, I don't see any other matching factors. This would be a great strategy, hint, hint, wink, wink, when we get to a test question like this. Sometimes there are more answers than 3, sometimes there are fewer answers than 3. It really depends on what ratio we're starting with. This last one that you had to do tonight is number 18. It says use multiplication to find 3 ratios. Ooh, this time we're using multiplication. We're finding 3 equivalent ratios. I'll kind of code that. We're looking for 3 of them. And we're starting with 5 to 11. Oh, darn it. I could make T-charts all day, but I noticed I would never find many common factors. Well, 1 goes into both. Oh, that's probably why we're not dividing this time. They said let's multiply. So this is just like our card game today in class, where we used 5 to 11, or we were given an original ratio, and we decided on our own rule. What could I multiply both 5 and 11 by to get to an equivalent ratio? Well, I hope you'd say, I could double both of them. I could multiply by 2 on both sides. Well, what is 5 times 2? 10. What is 11 times 2? 22. This is an equivalent ratio. And I know that because you use the same great rule with both terms. Let's try again. So starting again with 5 to 11. And you could start with this 10 to 22 and then multiply, but your numbers start to get really big really quickly. So I'm going to go back to the original ratio. And instead of multiplying by 2, let's try something else. How about 3? Well, what is 3 times 5? 15. And what is 3 times 11? 33. This is another equivalent ratio. You could also test this out. If you were to simplify these, they should take you right back to 5 to 11, which then shows that they are equivalent. Well, you're actually supposed to give me a third equivalent ratio, and I'm not sure I'm going to do that for you tonight because I do want you to do a little bit of this thinking on your own, of course, maybe even more than a little, a lot of it. So instead of multiplying by 3 on both sides, I want you to choose your own great rule. So we already tried 2's, and whatever I do to the left, I do to the right. We already tried 3, whatever I did to the left, I did to the right. You need to try your own rule of multiplication here, but make sure it's something we haven't tried yet, and make sure it's the same rule on the left and the right. Okay, we're trying to keep things equivalent. This ends our lesson 4.2 on equivalent ratios. We're going to save those word problems for the next time I see you, where we get to deal with a few more conversions and challenges when it comes to equivalence. But I think for today, this was some good review. Equivalent ratios, follow the same rule every time.